Now, I would like to welcome back our amazing speaker, Ovia Seshadri. Ovia is a respected research engineer at Coindcx, specializing in proof of work blockchains with a with a PhD in computer science and engineering from IIT Delhi. As the Chennai chapter lead, Ovia is dedicated to fostering the growth of blockchain community with extensive expertise and a passion for innovation. Ovia contributes to shaping the future of blockchain technology. Welcome back, Ovia. Over to you.
Hi, Bhavya. Thank you for the introduction. Hi, hello, everyone. Please mention in the chat box if you're joining for the first time or if you've been attending the last two sessions. Okay, so I'm just going to share my screen. Right. Okay. Yep. Can you all see my screen?
Yeah, we can.
All right. Okay, cool. Welcome back, everyone. This is the third session of our Solidity Bootcamp. In the first session, we saw Ethereum fundamentals. We learned about proof of stake, the consensus algorithm. We learned about the EVM. We learned about the various types of transactions, the structure of a transaction, how storage is done, what is an account, everything in week one. In week two, we moved. So let me just quickly run through what we did in week two. Yep. So in week two, we saw the types of read transactions, which are not really transactions on the chain, but we saw how the structure would be to invoke a read-only function. We saw how to create a wallet. We saw what a block explorer looks like for both the mainnet and the testnet, and we got some funds via the faucet. We saw what various IDs we can use for tools and IDs we can use to write Solidity programs, which is the language for developing smart contracts on EVM chains. And we said that we'll be exclusively using Remix for this bootcamp. And so we went ahead and connected, we saw how Remix looks. We connected Remix to our MetaMask accounts, and then we started working on Solidity. So in Solidity, we saw the structure of this Solidity contract. We saw what comments look like, and we went through the statements line by line. And so, yeah, we also saw a sample contract called storage, which was basically just storing a state variable int and getting and setting that variable. We saw how functions should be written. Now we'll go into some of the details on how functions are written. What global variables we can access in the Solidity functions that comes through transactions. We saw variables, constants, immutables. We saw what pure and view functions are. View is basically when you're reading into the state of the smart contract. Pure is when you don't touch, read, or write to the smart contract. We ended with visibility of functions. We saw that functions have 4 types of visibility: public, private, internal, and external. Public means anybody can access that function from anywhere, either like from outside the contract or from the inside the contract, or children can inherited contracts also can access them. Private is nobody can access them except functions inside the contract itself, that same contract. So internal functions are from inside the contract, and inherited contracts can read the function, and external is only when outside contracts can invoke that function. State variables, we saw that there are 3 types of visibilities: public, private, and internal, with the same meaning. So yeah, and then now we come into week 3. I'm just going to recap on some of the stuff that we already saw before, and then to this week we'll cover different types of data locations, just storage, call data, and memory. Talk about events, modifiers, errors. We'll go a little advanced. We'll talk about fallback and receive functions, which are specific to smart contract programming. We'll see how inheritance works in Solidity. We'll see shadowing. We'll see contract to contract calling, and we'll also see how contract can generate other contracts, deploy other contracts. Okay, so before that, let's just recap on some of the things that I mentioned in the last session. Also, the different types of data. We have two types of data: value type and reference type. Value type is when the memory size is known for that data type prior, and reference type is when it's dynamic and it is allotted at runtime. So value types, we saw different examples called bool, int, unsigned integer, enum, address. All of these are value types, and we saw examples of all of these contracts. And in address type, we saw that there are two types of data types for the address type, which is address and address payable. And the reference type is that is dynamically allocated is array, struct, and mapping. And we kind of briefly went into the contracts examples also. So I will just recap some of the reference types. Mainly, I'll go over mappings again. So let's start here for this week. So now mappings, as I said, are like a dictionary. They are key value pairs that is stored in the contract. So the mapping is defined like this with the mapping keyword, open parenthesis, the data type of the key value, the key, this symbol equal to and greater than, and the data type of the value. So this is one to many relationship, and this should always be unique. The actual value here should always be unique. So it's normal how a dictionary works, and it can be read in the square bracket notation, like how we do for arrays. So you can think of it as basically arrays or key values. So let's quickly look at an example of the key. Yeah. So we saw also how to connect to a local host. So today I'm going to connect to my local host where I've saved. So all the programs from last week have already been shared. So you can follow the Slack channel to get the code for all the programs that I used last week. So now today I'm going to be starting with mappings. So mapping, as I said, so this is just a sample contract to use mappings. Mapping is defined like this. That means my map is the variable name for the data type mapping, which stores keys as addresses and the corresponding values as integers, right? So let's see how this works. I mean, you can try and deploy it and play around with these functions. We saw how to deploy and use the functions on Remix using the local Remix VM. So you're not using MetaMask here, but you can also connect to, so when you deploy, you can, instead of choosing the Remix VM, you can also use an injected provider MetaMask, and automatically your contract will be deployed to the network that MetaMask is connected to, which is a separate test network for me. We covered all of this last class. You can use either way to check and play with these contracts, but I'm just going to be using Remix VM because it is faster. So this is the mapping. So we will be able, let me just deploy this. So after deploying, it's got an address here. The contract's name is mapping, and we have the functions. So this is public, so I can, and it's read only. So the Remix already automatically creates a getter for me. So if I give an address, I'll automatically get the corresponding uint value. And get is also a public function, so which is read only. It's a view function. So again, it is in blue. And there are two functions which change this my map, the state variable my map. So these are represented in orange, right? So yeah, so set will allow you to set a particular int value for a particular address, and remove will just delete the memory directly from in that position. So you can think of this as a two-dimensional array. Now, the nested mapping can be, you add another dimension of it. So you have a key as a data type like address, and the value is another mapping. So this is the nested form. We can also deploy this contract. So it's a good practice to have only one contract per Solidity file. But here, just to explain things easier and keep concepts in the same file, I've put both the mappings in this, both the contracts in the same file. So how do you deploy them? You have to deploy them each contract by contract. So the mapping contract is deployed. Now I can choose the nested mapping to deploy, and that is also deployed over here. So you can see there are two different mappings and in the two different deployments. Nested mapping also has the same set of functions. You can play around with them and figure out how it works. But this concept is it's there in almost all the new programming languages. So I'm not going to go into detail of this. Okay. So now coming to this, you might have seen, we have seen this diagram before. This is how Ethereum uses gas. Every piece of code. So in the transaction has some invocation. All the validator nodes have to verify a transaction, right? So the code, if let's say you're calling the function, let's say you're calling the function set, like we saw earlier. Setting means you're changing the some state variable. So that means the whole contract state, the blockchain state is changing. So any function invocation is, let me just, okay. Any function invocation is converted into a set of operations, and these operations are performed. So this we saw that this EVM is very much like any other virtual machine that we have studied before. But the only difference is every operation has an associated gas with it, and the gas is needed to preserve the validator's resources from malicious code. So now there are a set of operations that all code can be, can be drilled down to. Okay, so and each of those operations has an associated gas cost. So this is taken from the Ethereum yellow paper. You can also go and have a look at this. So every possible operation has has an associated gas cost with it. So as a Solidity developer, it is our job to write a code that converts into operations that have the least cost possible, that gets our the functionality that we want. So let's look at some ways to gas optimize based on the concepts that we already know. How can we write our code a little bit better? So gas optimization is a very vast and advanced topic, but I'm just giving you certain hints, just a flavor of it and how that can influence the way you think when writing this code. Right? So let's look at access. Okay, so so let's say that a contract, there are contract and there's a function. Let's say the get sum is the function, and get sum is the function that is invoked in a transaction, and that uses a state variable. Right? Now, when using a state variable, you're just reading from this. You're reading a state variable. So when loading the state variable for the first time, it's called cold access, cold load. But once it's already loaded into a cache or a fast access memory location, it is called a warm access. And cold access is always much more expensive than a warm access. It costs 2100 gas units, and warm access costs only 100 gas units. So it is always advisable to first, if you're going to do some like looping or some heavy operation with a state variable, copy it into a local memory first, then use it, and then put the final result back into the state variable. So that is exactly what this shows. So in the cold storage, so let's say that you don't copy it, you're using this my array, which has 10 elements, and get sum is basically summing up all the elements of the array. So now you're looping through this array, and for every loop, you are touching that state variable again and again. So you're hitting the cold access multiple times. So the total cost here estimate is 30,055 gas units. But if you see warm access, the warm access first copies this my array into local memory, and then loops through the local memory, which has significantly less gas cost, right? So this is what we want to aim. Like, let's write our code a little slightly better in a slightly different way so that we can improve the gas cost. So this was not, we cannot see this in our normal programming that we're used to in Web 2, right? Web 2, we think of space and time optimizations. So if you look at it, it's the same time complexity. It's not really changing much. You're still looping through the same amount of time, and it's not significantly, and actually here we're asking you to use extra memory. So you're using more space, but it's the same time. But here we have an additional dimension to consider other than space and time complexity. We have a cost complexity, if I can call it that, in the form of gas. So you have to keep this in mind. So now let's see another example. Funnily, in Solidity, changing a variable from 0 to non-zero values. That is, if it is 0 and you're changing it to non-zero, then it is a very expensive in terms of gas. Don't ask me why, but that's just how it is designed. But changing a variable from non-zero to 0 is relatively cheaper. So let's look at how this works in two different examples. Let's say that Nick has 10 tokens and Anna has 0 tokens. Now Nick has to send tokens to Anna. He wants to send all his tokens. That means we're updating the value from 10 to 0, and then Anna we're updating from 0 to 10. Okay. If you see, so in our example, non-zero to 0, that is, yeah, so 10 to 0. The non-zero to 0 part will cost only 5,000 gas. You can count the internal subdivisions later, but I'm telling you that it is 5,000 gas. And from 0 to non-zero will cost you 20,000 gas. So total, okay. Total gas is around 25,000, but in the non-zero to 0 case, there's a refund, because changing a value from non-zero to 0 will give you gas value refund based on this opcode RS clear. There is a discount on the execution price. So this contract is much cheaper than this contract. So here what they're doing, they're only sending 5 tokens. So there is a 0 to non-zero cost. But this is not a non-zero to 0 cost. So there's no discount here. So this contract will be much more expensive. So if the moral here is, try to avoid this 0 to non-zero values. And if you do non-zero to 0 values, you might get a gas refund. So most of the case, it's unavoidable to set something to 0, but you can keep this in mind. Also, is there a question?
Yeah, Ovia, are you sharing some other screen, because you can just see the remix ID?
Oh, okay. All right. I didn't realize this.
Yeah.
I didn't realize this. Sorry about that. Okay. Can you see now?
Yes. Yeah.
Okay, I don't know how much of it was missed. I think from here, right? So I was just explaining that all the code is converted into operations. Each operation costs some gas. And I explained that the Ethereum yellow paper has how much gas that each operation can cost. So our job is to reduce that final amount of gas needed. So first technique we saw was cold storage and warm storage. In cold storage means the amount of gas that's needed to first access a variable from storage, and warm access is when you're just accessing it from the cached storage, which is called memory. So in cold access, we saw that if you're hitting, there's an array that is being looped, and for every loop, you're hitting the state variable, which is a cold access. So this is much more expensive than this part, which is a warm access, where you first copy the memory array into a local memory, and then you loop on it in the local memory. So that was the first gas optimization technique. The second one is, I mentioned that changing a value from 0 to a non-zero is very expensive. But when you change a value from non-zero back to 0, there is a refund possible. So try to use this technique to, whenever possible, to get this refund. So we're all caught up now. Sorry about that. So maybe Bhavya, you can please, if I forget to switch back from code to slide, just let me know.
Yeah, sure.
So another gas optimization technique is the order of the state variables. Okay, so if we, any storage, so the contract storage has a memory sector called storage, where there are different slots to store variables and other pieces of code. And each slot is of 32 bytes of size, right? So what we want to do is we want to optimize the way in which we add the mention these variables such that we are compacting them into that 32 byte of slot. Okay, so let me just give this example. Let's say that there's a contract over here and you want 3 state variables, one bool value, one unsigned integer of 256 and one address. The bool takes 1 byte of storage. The U256 we already saw yesterday, it takes 256 bits, which is 32 bytes, and address takes 20 bytes of storage. So, while going in order of storing them, it will put this bool state in the first slot, and then it cannot fit the number in the first slot because it takes 1 byte, and this value takes 32 bytes. So it will create a new slot for it and add the number over here. And in the third, since that slot 2 is also filled, when the third variable comes, it will take another slot and add it over here. So we're using 3 storage slots to when we're deploying this contract. But now a better way to write this would be to switch these two variables when we are writing the contract, right? So if we write bool and an address, in the first slot itself, bool will take 1 byte, address will take 20 bytes. So in the first slot, you're just using 21 bytes to store. And then the second slot is completely occupied by the number value. So this is one, and this matters because loading one slot takes 2100 units of gas. So if we write a contract like this, it'll reduce our gas cost. Another good optimization technique is, so it's better to define our integer values, unsigned integer, as 256 than unsigned integer 8. I mean, if you would say that unsigned integer 8 is just 8 bits, which is 1 byte, but 256 is 32 bytes. Why would you want to do that, right? It's a valid question. But what happens is, if you're not putting the slots properly, right? Let's go back to the previous slide. Here, if you don't have all of this and you just have one number, unsigned integer 8 will take up 1 slot, and the remaining 31 bytes of that slot is filled with 0, and there is a cost associated with filling it with 0. So that is why it takes actually more gas to store a variable of unsigned integer, provided there is no other variables. If you can compactly fit that unsigned integer 8, then it is totally fine. My gas optimization technique does not apply over here. But if you're only storing that unsigned integer in a complete slot, then it's better to just use unsigned integer 256 than unsigned integer 8. So I hope this helps. It's not all the techniques, obviously. I mean, we'll have to understand how Ethereum works on a deeper level to write the most efficient code. But this is in some ways you can think, and you can also go read up about it later, and you can appreciate how Solidity programming is slightly different from our traditional way of coding. Okay, now coming back to Solidity constructs, we will look at conditional construct, which is if, else, and loops. I'll just directly show you this in code. Okay, let me, yeah. So now Let me just open up this. Okay. If else is very similar to our other programming languages. You have if and then a condition, and then else if and else. You can have nested if else's. And you can also use the ternary operator, which is there in Python and other languages, where this is the condition. The condition is true, then return this value, else return that value. So the whole if else could also be written in a single line like this. Loops, we have for loops and we have while loops. For loops, we already know, like as in there's an initial condition, there is an initial initiation, and then there is a exit condition, and there is an increment value, and then this is the code of the loop. And while is, this is the entry condition, and then while this entry condition is satisfied, you keep executing that loop. So you be very careful, because if there is a problem in your loop, then of course your transaction will fail and your gas will also be lost. So be careful when you're writing loops. Loops in general should just be avoided, because I mean that you can find alternate ways to iterate through your arrays or mappings. But make sure that it is finite. You're not you have to avoid it as much as possible. Yep, coming back. Right. So now I want to go into we saw that the function has different properties. Let me just go back to where we define functions. Oh, no. Yeah. So we saw that functions have the function keyword followed by the function name, followed by a parameter list with the data type. It has visibility, which I saw was we saw was private, public, internal, external, modifiers, a return list, and a function body. So now we're going to look at modifiers and function selectors and errors in the next few slides. Okay, so coming to function selector. Okay, so now we know that functions are part of a Solidity contract and it is deployed on the chain. It exists on the chain, and we can invoke these functions through transactions. So we saw three types of transaction: value transfer, contract deployment, and contract invocation. The contract invocation is basically you calling a function and passing the necessary arguments to execute that function. So now when we're doing this, every function, so how do you pass the arguments? How do you tell in a transaction, how do you mention which contract, which function we're calling, and how do you pass the arguments? You do that by the function selector. Function selector is basically the signature of the function in a hashed format. So in a contract, let's say there's a function called transfer, which takes two parameters, which is first parameter is of the address type, and the second parameter is of the uint 256 type. So this whole thing hashed is called the function selector, right? The first 4 bytes of the call data in a transaction is basically the function selector always. So let's see how that is. So now here, let me just go to where, let's see. Okay, I'm in Etherscan, the main Etherscan over here. So let me just open some contract, random contract. Let's say I'm opening the Tether tokens. I'm looking at all the transactions here. And now there is a transfer transaction that has happened. Let's look at how this transaction has happened. So this is, I'm in the block explorer over here. I'm going to more details. And if you see, the function is transfer address and value, right? So now if you notice 0xa, this CBB, let's say it ends with CBB, this is the function selector. And for any transfer transactions across contracts, this will be the same function. If the signature is same, then the function selector will also be same. So just remember the CBB. Let us look at a different contract. I'm looking at, we saw USDT token. Let's look at some other token. Let's say Matic token. In Matic token, I'm again going to a transfer transaction. And if I go to the data over here, again, if you see, yes, it is the same function selector because the signature of the function does not change in across the same token contracts. They're all following a specific standard. So because the function signature is same, the selector is also same. After the selector, you are sending different input values. Here we need to send two input values. This is the first input value and the second input value. Together, all of this is basically the call data. We saw the structure of a transaction, right? So the call data is basically this part. Obviously it will not be sent like this. It will be sent in some format that we will not understand. It'll look something like this, which is basically the function signature followed by the first value followed by the second value. So this is what this is the encoding that is sent, and then the validators will know how to split this data and read it. Right. Okay. So coming back. Right. Okay. So this is all about function selectors. Let me see if I have some. Oh no. Yeah. So here, let me see if I have a selector. Yep. Okay. So yeah, how to create your own function selector? You can just so if you have a call data and you don't know if you don't know what the selector is, you can just like, this is how it's basically generated. It's basically, it takes a hash of it, converts it into bytes, takes a hash of it, and then takes the first 4 bytes. So if you have the entire call data and you want to just take the function selector part of it, and this is an example function that will help you do it, right? So let's try it. So if I'm just going to take, if I want to find the function selector of this, I'm just going to deploy this. Delete all my other deployed contracts. I'm going to deploy this, and there is a function selector over here. I'm going to give a string of the function signature. So if I give this string and get selector, what has happened? Did something happen? Yeah. So there's something different here. Oh no, I didn't paste it properly, guys. Sorry. Yeah. So if you see the transfer, is the screen visible, Bhavya? Is it too small?
It's readable, but if we can increase it by one size, that should be like good.
Okay. So is this fine?
Yeah.
So I've taken the entire function signature here and I've put it in this string function. So you can see that this is basically, it's converted into that CVB value we saw in Ether Block Explorer, right? So this is the function selector. Okay. Moving on. Let's see function modifiers. So in many functions in a contract, we may be checking the same values. For example, I have a contract where many functions, only the admin or the owner of the contract should be able to invoke it. So at the beginning of the function, you will write an if condition saying if it's only owner, only then you proceed with the rest of the code, right? So if this is like a precondition to the function. There can be some preconditions and there can be some post conditions. For example, if you want to set a lock, so that's that one variable can only be changed by one person at some point of time or something like that. So you want to set a lock before the function execution and then remove the lock after function completion, right? So these preconditions and post conditions can be set using a function modifier. So just basically the reusable code, you don't have to keep writing the same precondition and post condition. For example, the only owner condition, right? That can be used across many functions. So this modifier will let you write reusable code for preconditions and post conditions. So let's directly look at this with an example. Yep. Okay. So, okay. So here, So now I have a contract called function modifier, and there is an owner field here. And in the constructor, when I deploy this contract, the person who is deploying is automatically set as the owner. And now I have created a modifier. So let's say validate address is fine. Okay. So now let's say decrement, or let's say, okay, change owner. The function change owner can only be called by the current owner, right? Or no other person should be able to call it. So let's see, and I have created a modifier here. So modifier look very similar to functions with the keyword modifier and the modifier name. It can also take in some parameters if necessary. So now I've put a require message saying message.sender should be equal to owner. If not, then you pass it. You send back with an error saying not owner. So this is the only owner modifier. So now this modifier, so it always ends with underscore semicolon. Anything that is written above the underscore semicolon is the precondition for that function, and precondition for that modifier. Anything written after the underscore semicolon is the post condition. So now how do you use this modifier in a function? So now I want to say that the change owner function should be executed by only the owner. So in the function declaration, I have the function keyword, I have the name of the function, I have the parameter list, argument list with the data type. I've put the visibility as public. Now I'll put the list of modifiers that I need. That is, before this function executes, what all preconditions I need to check. So now only owner is one of the modifiers. You can add other modifiers just by space separated. You can add a list of modifiers, and the order in which the modifiers are executed are from right to left, from the last to the first. Here we only have one modifier, so that is fine. So before executing this line, it will go to the only owner modifier and execute this. And if there is an error here, then the function will automatically exit with this error. Right. So now it is also checking another set of modifiers. Sorry, there are two modifiers here. The second modifier is valid address. That is the address that you pass in this field, right, as an argument should be a valid address. That is not a zero address. So you're just checking that this also happens. So first you check this, and then you check this. And then if that is okay, then it'll allow you to change the state variable owner to the new owner who is sending this. So let us just quickly check this, whether this works or not. So I am first deploying the function modifier contract. I've deployed it. Now note the address of the person deploying. It is DC4. The person DC4 has deployed it. So that person has been set as the owner. So let us quickly check if the owner has been set correctly. So I'm just calling the owner, which is a getter, because it's a public state variable. And you can see that DC4 has been set. Now, if I change the address to some, let's say CB2, and I try to change the owner, firstly, I have to give some value. So let's just give some random address. Let's just give this random address. And if I say change owner, it will fail because with the error not an owner, because I changed the person who is invoking this function. The externally owned account that is invoking this function is not the owner. Now, if let's say okay, I'm just copying the CB2 copy. I go back to DC4, which is actually the owner, and then I change this here. I'm putting the CB2 address here and I change it. This executes. Why? Because from the owner address, I have invoked this function and I've passed another address. So the current owner, look at this, it's CD4 now. If I check it again, it has become CB2. Right. So this is how we change the owner of the contract, and by using modifiers. So I hope the concept of modifiers is clear. It is just to add preconditions and post conditions to our functions. Right, now coming back. Okay, events. So as we know that the blockchain network is kind of isolated. So you can deploy contracts to it, but the system itself cannot interact with any external servers or anything like that. It is closed off to the internet. All the data that can be accessed by any node on the inside the node blockchain network is other contracts that are already there, all the data items that are already there in the network. It cannot interact with any external server or data store. So, but we need to read from this blockchain, and we want to develop apps around it, which may use other servers, other database servers, like so DApps do have a combination of some data in centralized databases and some data that the user really values on the blockchain. So you need a way to connect to the outside world, is what I'm trying to say. And events allow the outside world to track something that happens on the blockchain. It allows the outside world to track any changes made on the blockchain. So events are like logs. So if something happens, a function is invoked, a state of a blockchain is changed, you can emit a log event, and you can emit an event also called a log, and other data stores, other servers which are reading can pick up these events and make changes accordingly. Right? So that is what events are. Let us look at events in example. Okay. Right. So now we have a contract event. Now so obviously this is just a test contract. So I have a function called test over here that are emitting different events. How do you write an event? So event has no body. It is just the keyword event and a name of the event. This is called log, but you can name the event whatever you want. And all the values that you want to be logged, that you want to be emitted as a log. So here so this event log, whenever you emit this event, it will basically send two values, one sender and one message, right? And there's another log which doesn't do anything, just does another log. So let's try this. So in a function test, I'm calling this event log, emitting it twice with different messages, and then I'm calling this another log also. So let us deploy this, delete all the other contracts. I'm going to deploy this contract. Now, in this, let me call the test event. So now the test should emit three things. And how do we read these logs? So when we call the function, that is a transaction, right? So the transaction, when it enters the block, there is a transaction receipt created, and these events can be read from there. So if I call this event, nothing happens here, but if you see, the transaction event has been created. And if you read it from here, this is the transaction hash from this address 5B3. Let's check that. Yes, 5B3. To the contract address, which is DAO, DA0, and this has how much gas it cost and all of that. And if you can see, there's a log here, and in the log you can see that there are three things. There is the event log has the message.sender and the hello world, and then there is another event log which has event message.sender and the string hello EVM. And then there is another log called another log which has 0 arguments. So this is how you can read logs. So this is how we read logs in Remix. Let's see how to do this in actual test network. So for now, just for this example, I'm going to be connecting to my injected provider MetaMask, and I'm going to deploy the same contract. So now it is asking me to sign, and I will pay my gas, confirm. I already have Sepolia ETH from the last session. So the transaction has gone through. I can check this transaction also that it is pending. I can speed it up by giving some more gas, but okay. So now it has gone through. Let me go to the Sepolia network. 1 second, where is it? Yeah, so this is my Sepolia network. So if you see, if I can just filter by my address. So now here I have performed a contract creation call, right? So the contract has been created. Okay. So now let us try to interact with this contract by calling the test function. Okay. Okay, I think I have to verify it to test it. So let's see if I can verify. Decompile by. I won't be able to interact with it directly from here. Yeah, it's a problem. Okay, let's interact it from with here. So now here I've deployed the contract. If I do a test. Okay, so I can interact with from here. I'm calling the event test again. I'll from my MetaMask, and has it gone through? It's still pending. Okay, it has gone through. Now I'm coming back to my Sepolia here and refreshing this. So you see that contract creation happened. Yeah, contract creation happened. Then now I've called the method test over here. So if I open this transaction, all the details are here. And in more details, if I see, you can see that there are even, where are they? Sorry, logs. If you can see logs over here, there are 3 logs that have been created. First log is, it is the message.sender and the message hello world. The second log is, name is log, it's hello EVM. And the third log is, the name is another log, which is not coming up over here. I think this is the topic, the hash of this signature of this. So yeah, we've got 3 logs. Yeah, so we've got 3 events that are created with this. So you can see this log is very useful for, it's almost there for every function. Even in the main, I'm coming to the main net over here. So if I go to the main, this is the main net. If I open any of the tokens, let's say USDT, in any of the transfer event, there will always be logs. So this is a transaction that has happened, a transfer transaction that has happened. You can see that it also has a log. That is who sent what, who sent whom, how much. So that is always logged in any transfer event that is called. So this is all about events. Right. Now moving on to errors. So there are 3 types of errors that we can write in Solidity. First is the revert error. So this is to explicitly just revert. So if you want to stop the flow of the contract, you can just say, you can just put it as revert, and you can just stop the execution at that point of time and revert any change. So the entire transaction is reverted, but the gas used till that point is consumed. Require error is you check a condition. If the condition is false, then you revert. If it is true, then you just proceed with the execution. Right? So you can check preconditions. So it's usually used, you can use it directly in the function also, but it is usually used in modifiers. Assert statement is also to check into, so not many people use assert. You usually stick to require and revert, but assert is also like require when you check a condition and then you proceed if it is correct. If it's true, then you proceed. Otherwise, it's an issue and the transaction is reverted. Apart from this, you can also write custom errors. So let's see how to do that. Right. So coming back to our remix. All right. So here. So in this contract error, we are checking 3 things. Okay, before we see custom errors, let's first see this example of the 3 types. Okay, so here I have an example. So there is a function called divide, which if we're going to call this function, we cannot give the denominator as 0. So you're just doing a require statement here. If b is not equal to 0, if this is false, that means b is equal to 0, then division by 0 is not allowed. Otherwise, you can just perform the division. Assert, you would write something like this, where you can put a condition. If the condition is true, then the execution proceeds. Otherwise, it reverts at this point. Otherwise, you can just do a blunt revert without any condition, just give the message on why you're reverting. But in all the cases, the transaction execution proceeds till that step and the gas consumed is gone. You won't get it back. So now let's see how to write custom errors. So here, a custom error is also a revert, but you can set the message at runtime, like if you want to pass a parameter or something like that. So here there is a contract called error with an address owner. Now let's see how they have. Yeah, so they have created an error here. There's a custom error here. Custom error is very similar to events. So you, instead of the keyword error, you have event, you have the keyword error, you have the name of the error and what you exactly want to pass in the error. So these values you only get at runtime. So this is why it's custom error. It's like custom revert statements. So you can revert with the error name and pass in whatever you want to pass at the time when you're actually reverting. So these are custom errors. Okay. Right. Okay, so now we're going on to storage paths, storage types in Solidity. Maybe I can say that. So these are, so when dealing with Solidity, you have, yeah, is there a question?
I know, I just saying we should like start to wind up since it's 9:15. Yeah.
Okay, cool. I'll try to finish a little more and then we'll wind up. Thanks, Bhavya. So type 3 ways where we can store data, members, and variables in Solidity are call data, storage, and memory. So I'll tell you what these mean, but you should not confuse yourself in using them. The best way is to not explicitly define them at all, because Solidity is improved enough to automatically allocate. But there are special cases where you need to explicitly say whether a variable is of memory or storage or call data. And that is a slightly advanced technique. But for now, when you're writing, you don't really need to mention, unless the IDE throws an error, and then you can see if it is needed or not. So call data is basically anything that comes with the invocation. It is, so in transaction, there is a special field called call data. Anything that comes there, right, that is called call data. That has a special place in memory where it is stored, and it cannot be changed. Whatever comes in call data is like fixed. You can read from it, but you cannot change the values that are stored in call data. By default, anything that comes in function arguments is stored under the call data segment in memory. So that's basically what call data is. Let us see a quick example. Yeah. So here, right, so there are 2 ways in which you can call data. You can directly, without passing anything in the function, you can directly pass the bytes in the call data and tell your function to read from the 4th byte. Obviously, the first 4 bytes are for the function selectors. From the 4th byte is the call data. So you're basically asking them to take the value A from the 4th byte of the call data. So it will start reading the 32 bytes after the 4th byte, from the 4th byte. And then you're saying another variable starts at the 36th byte. So these are the different way you can call, you can basically read from the call data directly in your function without passing it as parameters. Another way is when you pass it as parameters and explicitly define it as call data. So there are two parameters here. Param1 is implicitly stored in the call data part only, but here when you explicitly write call data, it cannot be changed. So here, this is basically a function that will convert an integer into string and return it. This is a helper function that basically changes the integer to string. So it basically says the result is the string with whatever you've passed in integer converted to string with whatever you passed. So if you see that this parameter cannot be changed in the function, but the result can be stored in some other in memory. We'll see what memory is next. So this is how you would explicitly write call data, but implicitly anything that comes here is automatically call data. So you don't have to explicitly write it. Okay, now coming to memory. So all you have to remember about call data is the data that is passed to the function that comes in the call data part of the transaction is stored in the under call data in memory. Okay. So next type is memory. Memory is all the variables, all the data elements that you want to store just for the execution part. It's not going to go into the permanent storage, which is the blockchain storage. It's not going to go into the blockchain. It's not a state variable. So any intermediate values that you need during your function execution, it is automatically stored as memory. Okay, and memory is more often you will be explicitly using the keyword memory to use this memory data point. So let's see how memory works. So here I have a contract here, memory contract, to concatenate two strings. So I'm accepting two strings over here. By default, these strings would be call data type, but I am explicitly writing them as memory because I don't want to store it in memory variable, which might in call data, which might not be so efficient. So I'm explicitly saying memory over here, and the result is also in memory because it's a pure function. You're not writing it back into the smart contract. So the execution, this variable dies after the execution of this function. So this is just another way of concatenating both the strings and converting it into bytes. It's a pretty lengthy way, and then the result is returned. Concatenation of both the string is returned, which is also a memory. So after the execution of this function, all of these memory positions are cleared. So this is the memory data location. Coming to the next type is the storage. Now, storage is everything that is written to the smart contract. So if you are using a variable that is ultimately written to the smart contract, then you will have to write it as storage. By default, when you're deploying the smart contract, all the state variables are stored in the storage part of the memory. So again, you don't have to explicitly write it. If you look at the contract, see, this is a storage contract. This is a state variable. Because it is a state variable, that is, it's in permanent memory, that is, it's stored on the blockchain. It is automatically in the storage part. So any memory location which you are ultimately, any reference type that you're ultimately storing in the blockchain, it has to be explicitly written as storage. Value types are okay because whenever you do assignments, value type is copied into a new memory location. So at that time, it doesn't matter. But if you're doing a reference type, if you're using an intermediary value, which is a reference type, which is ultimately stored into the blockchain, you have to explicitly write storage in front of it. Yeah, but as I said, don't explicitly write anything unless you're sure of what you're doing. It is optimized in a way that all of this is handled internally. Okay, let's go back. Fallback functions. Fallback functions is a very interesting new concept that is only there in Solidity. So let's say that you are invoking a contract. You have some address and you want to invoke a function in that address. If you haven't checked properly what function, if you don't know what contract you're calling, then you might be calling a contract which doesn't really have that function, because as I said, you don't have to even pass the parameters. You can just write a bunch of bytes in the call data and send your transaction. It'll ultimately hit the contract, but if it doesn't have it, the contract itself might not exist, or the function in that contract signature, function selector that you're passing might not exist. So in these cases, it'll be nice if the contract has a fallback functions. If it receives any transaction request invocation which it cannot process, then automatically that request is sent to the fallback function. That is the purpose of the fallback function. So let us see an example. There is a special type of fallback function called receive function. Now, receive function is also a fallback function, but if the function invocation has a value field, that is, the structure of a transaction has something called value, right? That means when you're sending native tokens or when you're sending ETH. So if that values field is not empty, and then it has come to a contract which it cannot recognize the function selector, then the receive function is invoked. So basically a payable fallback function is a receive function. It's better to write them separately. And this is a new concept that is introduced in later in Solidity. So if you have a value field in the function and there is only a fallback function and not a reverse receive function, then it's an error. It'll throw an error. So better you write a fallback and a receive function. So let us see this in example. Okay, so now this is the fallback. So here you see that, so there is a contract called fallback. Now it has an event. So it has a fallback and a receive here. So now if I'm trying to invoke, a nice thing in Solidity is that you can do console.logs. At least Remix supports that. So you can just import this library hardhat/console.log, and like you do in JavaScript, you can just write console log statements and you'll be able to see it. Okay, I haven't done it here, but I will show you another example where I use it. So here I'm trying to see, this contract sent to fallback. Let's say I'm calling this transfer to fallback function with the address of the other function, which does not have the method. So automatically it will go to the fallback function. Let's see if that happens. Or I'll let you guys experiment with this since we're running out of time. You let me know if you can understand this concept, if you can get this contract working and what exactly is happening. You can write a console.log statements and see what is happening. And next session, if we're not able to figure this out, then I will come back to it. Okay. Right. So I think today we can finish inheritance, and then and after that I'll stop, and then we'll take contract to contract calling, creating another contract, that is factory contracts, in the next session. So we're going to switch up the order a little bit. The hands-on project that we're doing, everything that is needed for that project is already covered in Solidity. So we will go ahead and do the hands-on project in the next session. Either me or a guest speaker will come to do that for you. It's going to be interesting. And then we will cover the remaining aspects of Solidity, like standards like ERC 20, ERC 721, ERC 1155. All of this, we'll look at some really good projects for all of these. We'll look at what stable coins are. We'll talk a little bit about DeFi. All of that we'll cover in the 5th session. So in the next session, we'll do the hands-on project, because all of these concepts are fresh in your head. It's already been taught. That's all you need to basically build that contract. So we will just go ahead with the hands-on project. So yeah, let me talk about inheritance and then we'll stop it. Inheritance is an age-old concept in computer science. It's been there in object-oriented programming. It is, yeah, most of you might be aware of inheritance already. It's basically a parent-child relationship. There can be a class or contract here, and there can be a child contract that inherits from the parent contract. When you say inherit, it will inherit all the state variables and the functions. So you'll be able to invoke all the parent variables and functions in the child contract. So this is how it is. How would you do inheritance? You have to use the keyword is in the contract that is inheriting from another contract. So child is a parent. Also, you can in many other languages, this is not possible, but it's possible here. Solidity supports multiple inheritance. So one contract can inherit from multiple contracts. So this is all about inheritance. Let's see it with a quick example. Right. Yeah, so let's see. So this basically, I hope you can see my screen. So this is the kind of inheritance we're going to do. We have like several contracts, A, B, C, D, E, F. Now each contract is going to be inheriting. So this line basically says that B is inheriting from A, C is inheriting from A, D and E are both inheriting from B and C, and F is inheriting only from B. So this is what the code has represented. So we have a contract A, which has a function foo, which returns A. Contract B is inheriting from A. So automatically the function foo has been inherited, but B has chosen to override this function with the same this thing. So when you call foo from contract B, this function is preceded. Like it will use this function. Yeah, so if you see that the keyword is used, this is the contract name and this is the name of the contract that it is inheriting from. C is also inheriting from A, like in the diagram. Now contract D is inheriting from B and C, and it is also overriding the foo function. Now, when D is created, the foo function of B, C, and A is available to D, but D has chosen to override it. So so D's function will be called. But if you see, D's foo function inherently calls the super foo function. So super will return the function, the same function of the immediate parent class. So now if you see that this foo function is overriding from B comma C, right? So now, as I said, the execution is always from right to left, and C is the first parent that has this foo function. So this foo function will be called on C from D. So let us check this. Let us deploy these contracts. So I have to deploy them in order because otherwise it will throw an error. So I'm deploying A first. Oh no, I'm still on MetaMask, which I don't want to do. Let's close this. Let's go back and change to Remix EVM, which is faster. You can do it in MetaMask also. I'm deployed A. Now let me deploy B. Now let me deploy C. Or I've deployed D by mistake. Did I deploy D? Yes, I deployed D. Let me cancel that. Right, so now I'll deploy C. Okay, now I'll deploy D. Actually, I don't have to deploy all of this, I think, because it will automatically take the code, because it's all in the same file. The code is visible to this contract. So I don't need to really deploy all the parents. It should automatically work. Let us test that theory. So now here, if I call foo, it should return C. That is our guess. So let us call foo and it has returned C. Correct. So let us try that theory where do all the functions, all the contracts need to be called only. So let's say I'm calling this D again, deployed. Now in D, if I call foo again, yeah. So this happens because I've written all the contracts in the same file. So when deploying D, automatically the code from the other contracts is also visible to it, and it's inherited from the same file. So if it was all in different files, then I would have had to write an import first, right? So yeah, this is how inheritance works. This code is self-explanatory. I'll let you play with it. So one more concept that I wanted to cover today was shadowing. Now shadowing, okay, interfaces also. So let's do interfaces or I'll leave interfaces to the next class because it's a little bit complicated. Let's do shadowing. Shadowing is basically when you have, so we know that variables have different scopes. So let's say there's a state variable or some functions that that a child class has inherited, and you have a local variable, right? And they have the same name, or the function has the same signature. Which one should the code pick? It'll automatically pick the one which is closest to it, like the innermost circle. So the local variable will always be preferred over the global variable. So that is called shadowing, and we must avoid it. So when you're writing your code, you should give unique names to all the variables so that you can differentiate from your state variables and the variables that you use locally. A good practice in Solidity is to use the underscore before a variable name to indicate that, let's say that if you have a parameter called owner, which is a state variable in your contract, and if you want to pass an address of the owner in a function, you write underscore, you name that parameter underscore owner, so you can differentiate between the owner variable of the function and the state variable owner. So that's why you write unique names for these variables. And yeah, so try to avoid shadowing at all costs. It's more recent versions of Solidity, it'll throw an error directly in your compiler, so you can check that out. So let's see. Okay. So here I have a contract A with a string called name. Now I have a get name function which takes in no parameters and it just returns the name. So now this contract C is inheriting from A, and it has a constructor which has, so now let's say that I don't have a constructor. Let me comment this. And if I just say c.getName, I have not done that, sorry. If I have a function that calls this get name, it will automatically return C, right? Okay, sorry. This is what
recording in progress.
Is there a question, Bhavya?
No, there's just a network issue.
Okay. So now if you see that I have a contract B, which is also inheriting from contract A, and I'm defining a variable called name here, which is contract B. But if you can see, Remix is throwing me an error because it is saying that the identifier is already declared. So you don't have to worry about Solidity because recent IDs, like, they throw an error. But even if they don't do it, you should avoid this practice. So this has thrown me an error. This will not compile. But if you do want to have a name which is separate, which is unique for this contract, you can just override the other name. So basically, you can just say that you can write a constructor which says the name is actually contract C. You can override it, and this is the correct way to do it. Right. So just a quick recap. Right. So today we saw some of the reference type variables. We saw some gas optimization techniques. We saw conditional statements. We saw what function selectors are, function modifiers, function events, what errors are, the 4 types, that is revert, require, assert, and custom errors. We saw the 3 types of memory locations called data storage and memory. And we saw what fallback functions are, receive functions. We saw what inheritance is. We'll cover interfaces in the next session, and we saw what shadowing is. So in the next session, we will cover interfaces. We will cover contract to contract calling, cover to contract creation from another contract, and then we will do a hands-on project. So I'll stop here. Any questions, Bhavya? Yeah, so there is a question by Sunil. How is the diamond problem addressed in Solidity inheritance? So the diamond problem basically exists because of overriding and all of those complications. That is all abstracted out. You have to basically write a clear code, because all these function variables are assigned at runtime. You will not face the diamond problem if you follow the rules of Solidity, rules of shadowing properly.
Hi. So I think, yeah, there was a network problem. Is the question answered? Hello. All right. Okay.
I hope it's answered. So the diamond problem is overriding. Like if you have multiple parents for a subclass, then and you call a function that exists in both class, you don't know which function to call, right? But here, as I said, in the order that you write them, the rightmost is taken, always it's preferred. So that is how the diamond problem is addressed. Okay. So then let's stop here for now. I think almost all the basic concepts of Solidity has already been covered. We have we've come through the bulk of it. So congratulations, guys. I hope you followed along, and I'll see you guys in the next session.